Olá, senhoras e senhores, eu sou Daniel Veiga, seu anfitrião da Riscos Brasil 2015 e agora nós vamos ver a palestra do Niels Jensen sobre a Caixa de ferramentas da gestão de riscos. Uma palestra diretamente da Dinamarca. Então, pegue seu papel e caneta, desligue seu celular e feche todas as abas do seu navegador para acompanhar tudo que ele tem a dizer. Essa palestra será legendada. Até mais!
Hello, my name is Niels Jensen, and today I want to talk to you about risk indices that need to be in your risk toolkit. After about 10 years with the Canadian petrochemical company Imperial Oil and 20 years at the Technical University of Denmark, I'm now the owner of SafePark, a small company in Slangerup, Denmark, involved in process safety issues. At Imperial, I learned that process safety and personal safety comes before anything else. At the Technical University of Denmark, I had the opportunity to use some of the tools I became familiar with in industry for the assessment of risk involved in experimental research activities, and also the opportunity to open the eyes of new engineering students for the importance of process safety in their coming careers in industry. The three risk indices this talk is concerned with are the Dow Chemical Exposure Index for evaluation of chemical exposure off-site, the Dow Fire and Explosion Index for evaluation of on-site risks of explosions and fires, and the ability of such events to impact delivery of products. And finally, the Likely Loss Fire and Explosion Index for situations where business interruption laws don't make sense. What are the major off-site risks in the process industry? They are, in my view, exposure to toxic chemicals and exposure to pressure waves from explosions. This talk focuses on exposure to toxic chemicals. For exposure to chemicals, I recommend you evaluate at least two scenarios. A worst-case scenario involving the largest on-site inventory of your most dangerous chemical, and a scenario featuring an event that is likely to occur on-site during normal operations or maintenance or other abnormal situation within a 5-year period. It is for the latter scenarios that the Dow Chemical Exposure Index, in my view, is an excellent tool. So let's take a closer look at that tool. The Dow Chemical Exposure Index was developed by the Dow Chemical Company in the mid-80s as a response to the release of metal isocyanate in Bhopal, India. It was to be used by plant engineers to estimate the possible consequences of releases from their unit, plant or site. The Chemical Exposure Index will give you a simple method to rate the relative acute health hazards to people in neighboring plants and communities from possible chemical releases from your plant. The Chemical Exposure Index is used when you conduct an initial process hazard analysis. In this connection, it serves as a screening tool for hazards requiring further study, such as a quantitative risk assessment. It is also a good tool for emergency response planning, where you are faced with questions such as shelter in place or evacuate, and how many to evacuate. To use this tool, you need the Dow Chemical Exposure Index Guide, which fortunately is available for free from the S2S website at www.safety-s2s.eu. You can also buy the guide online from Amazon and others. This slide shows the 7 steps in the Chemical Exposure Index calculation procedure. Likely the most challenging is the first step, definition of possible release scenarios, which is discussed in the following 2 slides. For some exotic chemicals, the second step could also require some creative thinking, and I will discuss that too. The third step is a simple release calculation using equations similar to the ones you have probably seen in your chemical Engineering Unit Operations textbook. The final 4 steps are trivial. The tank shown on the right of this slide shows 3 places where the content can be released without the tank bursting. From the nozzle at A, we can have a liquid release. From the nozzle at B, which is above the liquid level in the tank, we can have a gas release, and also from the safety valve at C, we can have a gas release. However, what happens to the material after it leaves the nozzle, especially at A, depends on the properties of the material being released and the conditions inside the tank and outside. Hence, the result can be a vapor cloud in a lake, or just a lake, as indicated in the figure at the bottom of this slide. If calculations from different units, plants, or sites across the world are to be compared, then it is necessary to define some standard release scenarios. This slide shows scenarios with release from process pipes of various sizes, from hoses, and from pressure relief devices. This slide continues with definition of standard release scenarios for vessels, spills, and tank overflows. Additional scenarios might apply to your site based on your experience and the technology you're using. Industrial hygienists have defined 3 different levels of harm from exposure to a toxic chemical. These definitions are shown on this slide. The concentrations are called Emergency Response Planning Guideline levels, or ERPG levels, and they are all 3 related to a 1-hour exposure. ERPG values are published by the American Industrial Hygiene Association. The concentration and severity of harm increases from ERPG 1 over ERPG 2 to ERPG 3. If no ERPG value are available, then estimated emergency planning guideline levels, or EEPG levels, are used. On the next slide, we'll see how these are estimated. To start an estimation of EEPGs, you need as a minimum a TWA, or time weighted average, for exposure of a worker over 8-hour work days for 5-day work weeks for 40 years of employment. If no such limit is available, then your industrial hygienist may be able to help you find a similar compound for which a TWA exists. The U.S. Department of Energy have also published what is called Temporary Emergency Response Emergency Exposure Limits, or TEALs, for use at their facilities when ERPGs are unavailable. The calculation of the amount of airborne material from a gaseous release is very simple, and some of you may recognize the form of the equation from your chemical engineering textbooks. The calculation of the amount airborne from a liquid release is more complicated because we have to account for both the possible creation of a lake and evaporation from this lake. On this and the following slide, the sub-steps for liquid release calculations are shown. First, here is the liquid release rate calculation. A release is assumed to last at least 900 seconds. If the tank runs empty before that time, then the release rate is the content of the tank divided by 900. Next, the maximum amount of possible pool content in a lake is simply the liquid release rate times 900 seconds, as the guide assumes the size of the lake has been stabilized after about 900 seconds, or a quarter of an hour. The amount of liquid which flashes upon release depends on the heat capacity of the liquid and the heat of evaporation of the liquid, the storage temperature of the liquid, and the normal boiling point of the liquid, as shown here. If you have no data for heat capacity and heat of evaporation, then a value of 0.0044 for the ratio may be used for many hydrocarbons. If the fraction flashed is greater than or equal to 0.2, then no lake is formed. The amount of airborne from the flash is a constant times the fraction flashed times the liquid release rate. The goal is to calculate the amount of evaporated from the lake formed. To do that, we need to know the amount of material in the lake, i.e. what was released minus what was initially flashed, and the surface area of the lake, i.e. the interface to the air. In the latter calculation, we assume the depth of the lake to be 0.01 meter or 1 centimeter. Naturally, if the lake is formed in a diked area, then the dike limits the surface area and the depth could be much more than 1 centimeter. Here is the semi-empirical equation for calculation of the amount evaporated from the lake. This calculation involves a characteristic pool temperature, which is defined on the next slide. This calculation is done, calculating the total amount of airborne is the sum of the amount flashed and the amount evaporated, subject to the constraint that it cannot exceed the liquid release rate calculated in the initial step. Finally, we can calculate the chemical exposure index and the hazard distances for the different emergency response planning guideline values. Not surprisingly, these equations have a similar form. At a workshop at Dow Chemical in Freeport some years ago, it was mentioned that a CE chemical exposure index of more than 200 required further risk analysis. Let us now consider an example. Let us consider chlorine sphere with a capacity of 1134 tons of chlorine and a 2-inch process supply line from the bottom of the sphere and a fill line with a similar diameter also terminating close to the bottom of the sphere. The sphere is operated at 5 degrees centigrade and a pressure of 332 kilopascal. The sphere is also equipped with a level alarm which alerts about the sphere being 90% full. Finally, on the top of the sphere there are 2 safety valves, both with a 1-inch opening. One is a gas safety valve which opens at 400 kilopascal, and the other is a liquid safety valve which opens at 450 kilopascal. What release scenarios are relevant for this tank? On this slide, the relevant release scenarios are listed. If the 2-inch nozzle on either the process supply line or on the process supply line to the consuming process or the fill line fails, then we are faced with a liquid chlorine release resulting in a pool and a chlorine vapor cloud. If the liquid safety valve opens, the release rate will be smaller than that of either of the 2-inch nozzles, and hence we don't need to calculate that scenario. Although the release rate from the gas safety valve, based on experience, also will be smaller, we will calculate this in order to confirm our assumption. Hence we can calculate at this point, we can already at this point eliminate the scenario where no vapor cloud is formed, based on the properties of chlorine. Here are the input data to the liquid release rate calculations listed. Property data such as liquid density can be obtained from the scientific literature or from your chlorine supplier. The liquid chlorine release rate is calculated to be 60 kilograms per second, and the total amount released in 900 seconds is about 54 tons, which is significantly smaller than the capacity of the sphere. Hence, we confirm that the assumption built into the equation of liquid release rate that the level in the tank is almost constant during the release holds in this case. Since the chlorine is boiling at minus 34 degrees centigrade and the temperature in the tank is plus 5 degrees centigrade, then the heat of evaporation should be calculated at a temperature of minus 15 degrees centigrade. We actually have two sources of information for heat of evaporation. One is the S2S safety website and another is the Riscos website. The curve shown here is created from the S2S website data. The two sources give identical results, so we use the value from the S2S website. This slide shows the flash and pool calculations. The fraction flash is 0.129 and hence the pool is formed. The airborne from the flash rate is 38.68 kilograms per second. The pool contains almost 40 to 20 tons and covers an area of almost 1,200 or more than 1,200 square meters, equivalent to more than 20 badminton courts. The calculated amount airborne from the pool amounts to 23 kilograms per second, and the sum of the amount flashed and the amount evaporated exceed the liquid release rate. Hence, the total amount airborne is limited to the liquid release rate as indicated here. The equation gives a chemical exposure index value exceeding the reliability range of the equations, which the creators of the index limits to values of 1000 for CEE. Or chemical exposure index. This slide shows the hazard distances for chlorine release. They are quite impressive, and again, the simplifying assumptions used in the derivation of the equations make us limit the less severe hazard distances to 10 kilometers. Based on these hazard distances, one could attempt to evacuate everyone within 6.5 kilometers of the release and ask people up to 10 kilometers away from the release to shelter in place. The ERPG values used in these calculations are respectively 3, 9, and 58 milligrams per cubic meter. Here are some suggestions for mitigating off-site risks. Distance is the absolute best. But we cannot think about prohibiting people from living within 6.5 kilometers of a facility. More realistic would be to attempt to maintain the facility so releases are less likely, and if they do happen, then have alert triggered in people's homes about a condition requiring sheltering in place. The question is, if a scenario such as the one used in this example is realistic. Unfortunately, the answer is yes. During the summer floods in Central Europe some years ago, a plant in the Czech Republic experienced a release of 80 tons of liquid chlorine. In that case, a cylindrical tank was partly filled with liquid chlorine, and the buoyancy forces were strong enough to separate the tank from its foundation and pull apart the piping from the tank to the process consuming the chlorine. Chlorine is a heavy gas which spread along the ground until it is sufficiently diluted. In the Czech Republic, the gas cloud lifted a few hundred meters from a small town which had not been evacuated. This slide summarizes the calculations for Caixa's chlorine release. We immediately notice this chemical exposure index and hazard distances are much smaller, although not insignificant. Finally, here's a summary of the CI calculations for chlorine releases. The calculation clearly shows that liquid chlorine releases are much more hazardous than a gas release. The liquid release considered here is rather large. Often liquid release starts with a very small release from a flange or a connection. Such liquid releases are easy to spot in humid areas of the world, since the evaporating chlorine cools the air and hence create a buildup of ice around the leakage. This buildup is easy to spot and take action on, much easier than an equally small gas release. However, since you do not know whether you will have a liquid or gaseous release of chlorine, your emergency response plans must consider both possibilities. The hazardous distance gives first steps in an emergency response plan for these scenarios. Next step is to consider possible actions to take to prevent either release from occurring. This ends the coverage of the Chemical Exposure Index for off-site assessment of chemical releases. Let us next turn to major on-site hazards. A hazardous event usually starts with the release of a toxic or flammable material. The Chemical Exposure Index, which we have just talked about, deals with the toxic effects. Other possible consequences are explosions, which are often followed by fires. As you know, ignition sources is something you does not have to pay for even in most chemical plants. A tool to perform analysis of the impact of explosion and fires is the index which we will now turn to. It is called the Dow Fire and Explosion Index. The Dow Fire and Explosion Index in its first form dates back to the early 60s. About the same time, ICI developed the idea of hazard and operability studies. The Fire and Explosion Index is a tool developed by the Dow Chemical Company to be used by plant engineers to assess the potential for loss caused by explosions and fires and quantify the expected damage, and identify equipment that could contribute to escalation of an event. The Fire and Explosion Index gives a simple method for rating the hazard potential of a process unit, a plant, or a site. A tool to quantify the loss potential, and not least, a method to communicate the potential risk to management in order to secure investment in loss reduction measures. You should use the Fire and Explosion Index during the initial process hazard analysis as a screening tool for further studies of risk reduction initiatives and in emergency response planning. All you need to get started is the Dow Fire and Explosion Index Guide, which you can download from the S2S website at www.safety-s2s.eu or buy from an online bookstore like Amazon. The Fire and Explosion Index provides management with a uniform picture of the risk exposure in many different processes, sites, plants, and units, and hence facilitate the prioritization of investment in loss reduction measures. The application of the Fire and Explosion Index is a 7-step procedure for each unit, plant, or site involved. Selection of pertinent process units is the first step. Determination of material factor for each unit or plant is the second step. Third is calculation of the general process hazard factor, which I also call the design hazard factor. Fourth, the calculation of the special process hazard factor, which I call the operations hazard factor. And fifth, determination of the process unit hazard factor and calculation of the fire and explosion index as a measure of the hazard level of the unit or plant or site. Finally, 6, estimate the loss protection credit for each unit or process or plant. And 7, estimate the potential production outage and business loss. And finally, review and prioritize loss reduction investment based on the results. This slide is an overview of the fire and explosion index calculation procedure. The fire and explosion index procedure can be divided into 2 parts. The first part, shown here in orange, is concerned with the hazard level in the process unit or plant or site. The second part, shown here in blue, is concerned with the potential risk to the business in terms such as production losses and financial losses. A so-called pertinent process unit is a unit in which the material has a high material factor or a high quantity of materials is involved, or expensive equipment is involved, or extreme operating conditions are involved, or past history of incidents is available, or is critical to the site's operation. An example of the latter is the thermal oxidizer. You might want to involve your operators in the selection of pertinent process units. After a process unit is selected, we need to determine the material factor, which is a measure of the energy potential of the material processed in the unit. The material factor is based on flammability and reactivity ratings, which can be found in the Fire and Explosion Index Guide or in publications from the National Fire Protection Association, NFPA. Reactivity can also be estimated from laboratory measurements by measuring the decomposition exotherms as shown here. The material factor can only have values of 1, 4, 10, 14, 16, 21, 24, 29, or 40. This table shows how it is determined from the flammability rating in F and the reactivity rating in R for liquids and gases. For example, methanol, which has a flammability rating of 3 and a reactivity rating of 0, has a material factor of 16, i.e. moderate. The table in this slide shows the determination of material factor for combustible dust, mists, and solids. KST is a standard measure of dust explosiveness. Experience has shown that under certain operating conditions, the material factor have to be increased. This table shows how this modification is done. Once the material factor has been determined, we can turn our attention to the general process hazard factor. The base factor is 1, and then penalties are added for the following design conditions: exothermic chemical reaction, endothermic chemical reaction, material handling and transfer, enclosed or indoor process unit, access to process area, drainage and spill control. Obviously, you need to read the detailed explanations for each of these items in the guide before attempting to assign penalties. Read the guide not just one time, but at least twice. And for your first attempt to assign penalties, discuss your suggested penalties with a colleague. The special process hazards factor also starts with a base factor of 1, and penalties are added for the following operating condition: toxic material, subatmospheric pressure, operation in or near flammable range, dust explosion, pressure, low temperature, or quantity of flammable and unstable material, corrosion or erosion, leakage at joints and packings, use of fired equipment, hot oil exchange systems, rotating equipment. Again, read the detailed explanations of each item in the guide before you try to assign penalties to any one thing. It is my experience that students, when first introduced to the Fire Explosion Index, assign too high penalties or miss that certain penalties exclude others. The Fire Explosion Index is simply the multiplication of the material factor by the general process hazards factor and by the special process hazards factor. If penalties are reasonably assigned, then the product of the two hazards factors should not exceed 8. It is strongly recommended to apply this limit in the calculations of your Fire and Explosion Index. The tables show the relation between the Fire and Explosion Index and the level or degree of hazard using the scale light, moderate, intermediate, heavy, and severe. Fire and Explosion Index values above 128 requires further risk assessment, for example, a quantitative risk assessment. We have now performed the hazard assessment shown here with the green line around it. We now turn to the risk assessment shown here with the purple line around it. A number of steps are involved, such as exposure area determination, value of equipment in exposure area, damage factor estimation, base maximum probable property damage, loss control credit calculation, actual maximum probable property damage, maximum probable days outage, and business interruption loss. The following slides briefly looks at each of these. The base maximum probable property damage is the damage estimate which don't consider any loss control measures taken at the site or plant. The value of the equipment is the original cost adjusted for inflation using the Chemical Engineering Plant Cost Index. A graph of the CEPCI is shown on the next slide. From this graph of the CEPCI, we see that during the financial crisis of recent years, the inflation was low. The loss control credit factor is the product of credit factors relating to 3 areas: control, isolation, and protection. The following slides list the items to be considered in determining each credit factor. Again, consult the guide for details about how and what to take credit for. Notice that credit factors are multiplicative, while hazard factors, as we used earlier, are additive. Items considered in the process control credit factor are emergency power, cooling, explosion control, emergency shutdown, computer control, inert gas, operating instructions and procedures, reactive chemicals review, other process hazards analysis. Other process hazards analysis could be any of the following activities: quantitative risk assessment, detailed consequence analysis, fault tree analysis, hazard studies, failure mode and effect analysis, what-if studies, checklist evaluations, management of change review, but only one factor can be applied for other process hazard analysis. Items considered in the material isolation credit factor are remote control valves, dump and blow down systems, drainage and interlock. Items considered in the protection credit factor are leak detection, structural steel protection, fire water supply, special systems, sprinkler systems, water curtains, foam, hand extinguishers and monitors, cable protection. Estimation of the actual maximum probable property damage and the business interruption losses are done on this slide. Notice that the guide is unclear about calculation of the maximum probable days outage. I suggest that the actual maximum probable property damage should be converted to $1986 in order to use the equations from the guide to estimate the maximum probable days outage. I simply don't believe that the maximum probable days outage should increase with inflation. Generally, fire and explosion index is used to adjust plant layout to have adequate separation between process units by drawing exposure circles on a preliminary plot plan. And naturally, business interruption losses are used to prioritize loss reduction investments As an example, we consider the determination of the fire and explosion index for a nitroaniline reactor. Such a reactor exploded on August 8, 1969 at a plant in the town of Sauget, about 6 kilometers south of St. Louis in Illinois, United States. The primary cause of the event was that too much aniline had been added to the reactor and its safety valve did not work. The temperature indicator in the control room was frozen at 194 degrees centigrade, and the operator did not know that the temperature continued to increase. The pressure indicator was also maxed out. The 3,350-gallon reactor was placed indoor with limited access. Normal operating temperature was 175 degrees centigrade, and the 2.5-inch thick reactor could easily withstand pressures up to 550 psig. Hence, the determination of the design hazard factor for the nitroaniline reactor is shown here. This factor amounts to 3.1. And here the determination of the operation hazard factor for the aniline reactor is shown. This factor amounts to 3.5. The product of these exceed 8, and hence the unit hazard factor is limited to 8. The result is a fire and explosion index of 128, which indicates a serious fire and explosion hazard. The radius of exposure is approximately 33 meters. The base maximum probable property damage is $23 million and a damage factor of based on a damage factor of 0.68. Loss control credits could not be calculated, and this results in therefore in an estimated outage of between 80 and 60 days. Could your facility survive such an outage? This concludes our coverage of the Fire and Explosion Index. Finally, we will look at a likely loss fire and explosion index. There are situations in which items such as business interruption loss and maximum probable property damage or actual or base doesn't make any sense. It is for these situations that the likely loss fire and explosion index has been created. It is to be applied where equipment damage and business interruption loss is not relevant, such as in pilot plants at universities and other research facilities. The procedure from the Fire and Explosion Index is used in the hazard estimation step, i.e. the first part of the procedure, but an alternative approach is taken with the risk assessment. This is a plot of damage factor versus material factor with unit hazard factor as a parameter. This is taken from the Dow guide. The material factor can only have the values of 1, 4, 10, 14, 16, 21, 24, 29, and 30. The unit process hazard factor, however, can have many values between 1 and 8, although it is not continuous. So what results if we interchange the two parameters which the damage factor depends on? As you can see, the relation between damage factor and unit hazard factor is much more linear than the relation between damage factor and material factor. The lines for the different material factors are close to parallel. So what happens if we normalize with the material factor? Except for the line with the lowest material factor, the normalization results in lines lying in a narrow band and with a clear upper bound. Hence, we ignore the lowest material factor and find an equation for the upper bound on the damage factor as a function of unit hazard factor. This slide shows some of the thinking behind the likely loss fire and explosion index and how this index is just a function of the fire and explosion index, the damage factor, and the loss control credit factor. The likely loss fire and explosion index has been designed to always be lower than the fire and explosion index. The risk levels corresponding to the hazard levels of the fire explosion index are indicated in the table on this slide. Here the likely loss fire explosion index is applied to two pilot plants at the Department of Chemical Engineering at the Technical University of Denmark. The reactor with recirculation of unreacted material and a distillation column with reuse of condenser heat in the reboiler. Both were judged to be acceptable risk in the academic environments before the likely loss fire and explosion index was developed. The likely loss fire and explosion index confirmed this judgment. In this talk, you have been introduced to three indices which you can use in hazard and risk assessment for on-site and off-site events. You have received detailed instructions on the use of the Dow Chemical Exposure Index for both gas and liquid releases. You have received an introduction and overview of how to use the Dow Fire and Explosion Index to optimize your plant layout to reduce consequences of fires and explosions and to prioritize your investment in loss reduction. You have been briefly introduced to the likely loss fire explosion index for cases where fire hazards and risk are more important than dollars. Have a good day.
Olá, senhoras e senhores! Espero que você tenha gostado de assistir essa palestra com um excelente conteúdo da Riscos Brasil 2015. Caso você esteja cadastrado na nossa lista, você está recebendo os horários das exibições gratuitas. E se mesmo assim você não conseguiu assistir alguma palestra, não tem problema, porque você pode adquirir o pacote VIP da Riscos. Com o pacote VIP você tem acesso a todas as palestras no ambiente de EAD, para assistir as palestras quando quiser, quantas vezes quiser, durante 2 anos. Então, clique no botão que aparece aqui na sua tela e adquira já o seu pacote VIP para ter acesso a todas as palestras e assistir tranquilamente a hora que você quiser. Até mais!